Now this model is a little bit more difficult than the other models that I have been diagnosing up till now. This is why I first will show you the correct model, and then I will go to my faulty variant of it. This model tries to represent the oscillation of a spring. The spring has a certain weight, which has both the momentum and the position, as you can see here. We assume that the experiment takes place on planet Earth, and planet Earth obviously has some gravity, and we have set gravity to an exogenous value so that it will stay steady throughout the simulation. Also, the spring itself has an elasticity, and then we have some model fragments. First of all, we have the model fragment of the spring, which shows the relation between the position of the weight and the elasticity of the spring, right? So negatively proportional. We have another model fragment about elasticity, which positively influences the momentum of the weight, right? Then we have the third model fragment about the momentum and its relation to the position of the weight. And then the fourth and last model fragment is about the gravity, which itself influences momentum. Okay, if we simulate this, and remember this is the correct model and therefore also the correct simulation results, we get something that looks a little like a cycle. Let me select one possible walkthrough and plot the values. What you see is the idea of simulating the elasticity of a spring, which means that the momentum goes first down and then goes up like this, and at the same time the position of the weight is decreasing. At some point it's steady and then it's increasing, and this is mirrored by the elasticity of the spring, which goes exactly the other way around. Gravity, we need not talk about that because of its exogenous value. It will remain the same value throughout the simulation. Okay, so let's look at this little model now, and let's run a simulation. And as you can see, we do not get the same state growth. Now let's see what we do get. What we do get is gravity is obviously the same. Momentum, let's compare the momentum. What you see is that momentum is also the same, right? So momentum is going down, and at some point in the third state it is steady. But what is different is that elasticity and position, both of them are already steady, and this is not what we want. We want position to decrease further and elasticity to increase further. So this is my expectation in the diagnosis. I say the third state, elasticity is increasing. I stage this expectation, and now my second expectation in the third state, position is decreasing, and I stage that expectation as well. I now run the diagnosis, and as you see, it asks me another question. It asks me, what do you expect that the derivative of the momentum is in state 3? Well, let's see. The derivative of the momentum in state 3 should be steady, right? This is completely in agreement with the simulation results. I press continue, and now the diagnosis has identified a possible fault, which is momentum is proportional to position. So let's look at that model fragment. Momentum being proportional to position. And let's give this a little bit of thought. Why would this be wrong? If the momentum is positive, then position should increase, right? So it should not be a proportionality, but rather an influence. Let's compare this to the correct model, which I showed you in the beginning, and you can see that this indeed is the discrepancy between the correct and the faulty model. Now, this was kind of a difficult diagnosis, but this was done in order to make you appreciate the difficulty of the culprits that can be found by using the diagnosis, and maybe some culprits that would otherwise have taken several minutes even for an expert to identify.